Today we're learning about similar shapes and we're looking at the lengths of the sides of those similar shapes. So for your starter, I'm just going to ask you to write down 5 things on some scrap paper that you notice about the images here, and then we'll talk in a second about how they relate to similar shapes. Okay, so hopefully one of the things that you've noticed is that this photo here and this one here are exactly the same measurements. The only change between this picture and this picture is that this one's been rotated 90 degrees to the left. When things are absolutely identical, we call that congruent. You might also have noticed that we've got another rotation here. However, all the dimensions have been doubled. So 3.5 for the height of the photo has been doubled to get 7, and 5 for the width has been doubled to make 10. And when every dimension has been doubled like that, we call that similar. It could have been multiplied by any amounts, so all of these dimensions could have been multiplied by 3 or 10 or 1.2. As long as every dimension has been multiplied by the same amount, that's what makes it similar. Then you might notice that this photo, it just looks a little bit strange. It's been squashed in some way. And that's because rather than multiplying the measurements, here there's been a centimetre added to each of those measurements. And just adding on a centimetre doesn't keep the original perspective and the proportions of the photo correct, which is why it looks a little bit strange. So we now know a little bit about similar shapes. Other things you might have noticed, obviously we've got snowboarder, that's Amy Fuller, it's her competing for the British team, and you might have just noticed something about the colours and the fact that all of these units are in centimetres as well. Okay, so a little bit of an introduction to similar shapes. We're going to make a note of this entire box here. So mathematically similar means that the angles between the two shapes are the same, but one is an enlargement of the other. So if we think about the previous example with the photos, it was 90 degrees in every corner of the photo and one was just larger than the other. So that means that similar triangles share the same angles, AAA for angle, 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 but that also means that regular polygons are mathematically similar as well. So every regular pentagon is similar to every other regular pentagon because they all have to have the same angles. Every square would be similar to every other square. Every equilateral triangle would be similar to every equilateral triangle. So remembering that regular means that the angles have to be equal and the side lengths are equal in those shapes. This would actually also be true for a circle as well. Okay, so scale factor. We looked at that when we did enlargement, so we already know that we have to find corresponding sides, the ones that are in the same position. We can't take the width of one and the height of the other, for example. We use the formula scale factor equals 2 over from, but because this time we might be going forwards and backwards quite a lot, rather than having to rework out the scale factor once we've done it one way, you can just find the inverse scale factor by doing the reciprocal. And hopefully you remembered that the word reciprocal just means that it's the flipped upside down of the fraction. So pause the video, take a few notes here, and then we'll move on. Okay, so here we've got 2 similar triangles, and the reason that we know that they're similar is because they've marked that this angle equals this one, and this angle equals this one. And because of the fact that angles in a triangle add up to 180, if 2 of them are the same, that means the last one is the same as well. So the first thing that we're going to do is we're going to get 3 colours of highlighter out and match up which are the corresponding sides. Now it seems quite straightforward on this example, but you are going to do some in the future where one's one direction and one is another, so it's just a useful habit to get into. So this side connecting the single angle with the double angle matches with the corresponding side there. We've got the single angle to the unlabelled matching up here, and then we have the final side matching up there as well. Okay, so looking through all of those sides, the first thing we need to do now, once we've labelled, is to get the scale factor. So we know that scale factor is 2 over from, and we've got to find the sides marked Y and Z. So I'm going to start by trying to find y. So that means I'm going 2y from this shape here. So I'm just going to draw an arrow on there to say which way I'm going. I've then got to work out which side I can use to find the scale factor. So is it the green side, is it the blue side, or is it the red side? And of course I need to know the measurement for both shapes on the side that I pick. So blue is no good, I've only got one measurement. Red is no good, only one measurement, but I have got both measurements here on the green. So using that green side, I'm going to calculate my scale factor, which is 2 over from. So I'm going 2, the larger shape, 11.2, from the smaller shape, which is 8. Now, depending on whether you have a calculator or not, you might have to leave the scale factor as a fraction. So even though I'm going to type this into my calculator now, I'm going to simplify it into the fraction 7 over 5. You could do that without a calculator, of course. You could times top and bottom by 10 to get whole numbers and then just simplify all the way down. Okay, so now we have a scale factor. I'm going to find shape y, the length of y. So y is going to be the original blue measurement from the smaller shape multiplied going this way by the scale factor that we've just had. So it's going to be 4.5 times by 7 over 5, and that is going to give me 6.3 centimetres for the length of y. Okay, next up then I'm going to find z, but I might just have spotted that for z I'm not going in the same direction that I just did. I was going from the small shape to the big shape, but for z I'm going to need to go from the big to the small, and this is where that inverse scale factor comes in. So it's going to be 8.4, but rather than timesing by 7 over 5, I'm going to multiply by the inverse scale factor, so 5 over 7, just flipping that fraction upside down, and that gives me 6 centimetres. Okay, so let's see how you got on with that so far. So if we just look at this quick question, if you grab yourself some rough paper, see if you can answer what is the scale factor relating shape A to B, and what about B to A. So you might want to draw a quick sketch, highlight it, and then we're going to do some more examples in a second. Okay, so straight away looking at this, I can see that the side that I have corresponding on both shapes is the blue side. That's the only one where I have both measurements. So first of all, I'm going to do the scale factor relating A to B as I'm asked. So I'm going 2 over from, and I'm going 2B, so 12 from A, 15. I'm just going to simplify the fraction because I can see that numerator and denominator are divisible by 3, so that gives me 4/5 for the scale factor. Now, for B to A, remember I could work it out again, but I know that I can just use the inverse scale factor, which is a bit quicker, so I just do the reciprocal of 4/5, which is 5 over 4. Okay. Okay, so this time we haven't got any angles marked, but we are told that ABC and PQR are similar. So we can start off with our same process of highlighting. So base sides, I'm going to do blue. The more slanted side, I'm going to do green. And the remaining side, I'm going to do red. Okay, so question A asks us what is the scale factor from ABC to PQR? So looking through the shapes, my corresponding side is the blue side. That seems to be the tradition so far. So scale factor is 2 over from. So I'm going 2 PQR, so 6 over 4, which simplifying gives me 3 over 2. Okay, question B asks for the scale factor from PQR to ABC. So it's just the inverse scale factor, which we know is the reciprocal, 2 over 3. Okay, now on C, I'm going to calculate the length of side QR. So I'm going to triangle PQR, I'm going to say QR is the original red measurement of 12 multiplied by the scale factor that gets me 2 PQR. So that's what I did up here. So multiplying by 3 over 2. Now remember, we might be asked to do this without a calculator. So where we've got 12, we're going to turn that into 12 over 1. We can look for a little bit of cross cancelling here. So 12 and 2 are both divisible by 2. So I can make that 6 and 1. And then I get 6 times 3, 18. 1 times 1 is 1. And therefore it's 18 centimetres for my final answer. Okay, side AB, we're now going to the smaller shape, so my scale factor's going that way. So AB is the original green measurement of 15 times by the scale factor going to ABC. And I did 2 ABC just here. So multiplied by 2/3, and then same technique for the fractions as with question C. So make that over 1. Look for some cross cancelling. These are both divisible by 3, so that becomes 5 and 1. 5 times 2 is 10, 1 times 1 is 1, and 10 divided by 1 gives us 10. Okay, so in this final example, I just wanted to show to you it really doesn't need to just be triangles. It can be any shape that can be similar. So here we've got a straight side at the bottom, but a really wavy part for the rest of the shape. So reading through, shape A and shape B are similar, so there's our keyword telling us that we can use this technique. We're told the perimeter of shape A is 20, and we've got to find the perimeter of shape B. Okay, so remember with similar shapes, when we enlarge, it means that every single part of the shape's perimeter, every single side, or in this case curve, is going to be multiplied by the scale factor. So if we just look at this straight side, work out the scale factor, then we can apply that to the perimeter as well. So I'm going from shape A to shape B overall. So my scale factor, which is 2 over from, is going to be 6 over 5. And so that means that the perimeter of shape B is going to be the original perimeter of A, which was 20, multiplied by the scale factor, 6 over 5. And then we can just quickly do the same trick as, for example, 2 with the fractions. Make this over 1. Look for some cross cancelling, as these numbers are both divisible by 5. So that's 4 and 1. 4 times 6, 24. 1 times 1 is 1. So therefore the perimeter of shape B is 24 centimetres.